All right, so previously we determined that the average power was 2.5 milliwatts dissipated by that second resistor there, this one that we have circled. And now we want to basically just prove that we can take the average value of this signal and show mathematically that it is in fact 2.5 watts. You're not normally going to have to do all this. You can choose probably which one you prefer in order to find the average power. I just want to do it for the proof that it works. So again, the average power is going to be 1 over 2 pi times the integral from 0 to 2 pi, 2.5 times 1 minus the cosine of 2 omega t d omega t. And of course I can pull the 2.5 out, which is 5 halves, 5 over 2 pi. I can multiply the top and bottom by 2 if I wanted to, of 1 minus the cosine of 2 omega t d omega t. Okay, so we'll just leave that for now. It's going to be 5 halves over 2 pi. Actually, let's just leave it as 2.5. There's no reason to write it as a fraction. I didn't want to see a decimal, but I guess we'll just leave it. 2.5 over 2 pi. The integral of 1 is going to be omega t. The integral of the negative cosine term is going to be minus a half times the sine of 2 omega t. And this whole thing gets evaluated from 0 to 2 pi. Again, this is going to become 2.5 over 2 pi times 2 pi minus 1/2 the sine of 4 pi, which goes to 0, minus 0 minus 1/2 the sine of 0, which also goes to 0. We're left with the 2 pi's that cancel, and of course we get the same value, that P average is 2.5 milliwatts, which is exactly what we calculated previously. Okay, so that just kind of shows that we can do it either way, especially with the resistive load. Again, this is the more general way that you can always do it if you develop this expression for P of t properly. You can always take the integral, take the average value of that signal, and that's going to give you the average power. If you wish to do the IRMS, VRMS method, just be careful to note that IRMS times VRMS doesn't work unless the load is resistive, because there's an extra term that normally needs to be accounted for when the load is not resistive, which it most typically will not be purely resistive. Okay, so we're going to see that pretty soon. Now we're done with the resistive load example. This is a special case. The next video is going to be more generally showing you how you can calculate the average power when the load is any load, not just a resistive load. And I think you'll see why I've been making special mention of this case. And there's a new formula that we will use that will show that this is basically the special case, because we're going to add another term out here. And you'll see what happens when the load is resistive. That term basically goes to 1, and we are left with just this. Okay, so I'm going to go ahead and end this video. And in the next video, we're going to start talking about average power when the load is not purely resistive. Okay.